Lab 1 is due tonight at midnight. So that means that you need to have finished filling in all the boxes and stuff. Sometimes, it shouldn't be too easy to miss a question. I mean, miss as in not finish filling in all the questions. But you can always double check whether the system thinks you finished by going to your online assignments page, and it will tell you whether it thinks you completed the lab. And if it hasn't filled in the box with a completed date, then it doesn't think you completed the lab. So there is a late penalty associated with both the submission deadline and the checkoff deadline. You get sort of 1 point a day off up to the maximum points of the lab. However, the first 7 late days are a gift from us to you. So you can use them however you want. You can apply them all to one lab. You can spread them out and have your due date be on Fridays if that's what you like. The one deadline we can extend is the deadline for the final project, because that's right at the end of classes, and we can't make any extensions beyond the end of classes. Anyway, you have any issues or questions about penalties and deadlines and submission dates, just let me know. There is a checkoff meeting for each lab. We want to have a little conversation with you about the design problem. So it's very helpful if you can, before your checkoff, just refresh yourself. If you did the lab a while ago, perhaps, just refresh yourself about what you did and why, and you'll have it's not a high stakes question sort of thing. So you can just, if you did the work and you sort of remember what you did, you're good to go. So that's due on Wednesday. We can't check off everybody in the last hour on Wednesday. There are a lot of staff lab hours every week. There's lots and lots and lots of staff around. Check the lab hour schedule. So come in at a time when there's a lot of staff and that it's not right on the deadline, and you'll get checked off without a long wait. So, but if everybody shows up at Wednesday, 1 hour before, in the last staffed hour on Wednesday, we obviously are going to have a hard time getting everybody done then. So help us out and help yourself out. There's a quiz next Friday in section, so whatever section time you've been assigned, please go there. If you've been going to a different section than the registrar assigned you, that's fine. Just if you could just send me an email and let me know. My only goal is to try to make sure that everybody has a place to sit a week from Friday. And so obviously, again, if 300 people all show up at 11 a.m. in a particular room, we're not going to be able to meet that goal. Finally, we do have a makeup. The makeups are Monday, following the exam at 4 p.m. If absolutely necessary, we can accommodate a different makeup time. If you need a makeup, please get in touch. And the website suggests that Wednesday, you should get in touch by Wednesday so that we have enough time to make whatever arrangements we need. The same with an accommodation letter. You have an accommodation letter, sometimes they don't get them all issued right away. That's fine, but let me know if you need an accommodation, because again, I'd like a little bit of time to work out the details. In terms of needing a makeup, we're pretty flexible about what need means. You've been sick, you've had a busy week, L05 has a killer assignment due. Whatever your good reason is, that's fine. If taking the exam after the weekend is better for you, again, you need to ask, but once you ask, we're pretty accommodating. So keep that in mind. Alrighty, any questions about all this mechanics? We're sort of still in the first time through for everything. After this, it'll be all the rest of the labs and quizzes and checkoffs, and that's all. They're very much the same week to week. Okay, no questions. So today we get to introduce a new toy for us digital designers. We're going to introduce the notion of sequential logic, which, as we'll see, is fundamentally different than combinational logic. But a combination, no pun intended, of combinational logic and sequential logic is enough to build anything. Everything that you own is really a giant piece of sequential logic that has some combinational logic on the inside. So it's a good thing this is sort of the last major building block. We'll discuss some additional design techniques, but this is the last major circuit building block. So the thing we're going to discuss how to build today is the following box. We have a box, it has a switch, and it has a light. And if I press the switch, and if the light was off, the light will turn on. And then later, if I press the switch again, if the light was on, it will turn off. Okay, so this is not something we can build with combinational logic. So this circuit is different because it has two things. One, it has this notion of state. In other words, there was some notion that what happened when you pressed the switch, when you changed its input, depended on the history of inputs up to now. In other words, if there had been an even number of switches, the light was off. If there had been an odd number of button presses, so forget, I'm never going to get the odd and even right. But the notion is that the behavior of the box sort of depends on this notion of its current state. In other words, if the light is on when you press the switch, it does one thing. If the light is off when you press the switch, it does another. So we can't do that with combinational logic, because combinational logic, the output is always strictly a function of the instantaneous current value of the inputs. It doesn't depend on the history of the input. So we're going to start having this notion of keeping track of important things in the history and changing our behavior as a result. Okay, and the other thing we notice is that it's not a question of whether you're holding the button down and the light is on and then you let go and the light is off. That you could do with combinational logic. This has to do with sort of this notion of event, of a button push. So a combination of states and instance and time are really about what this lecture that's what this lecture is about. So the thing that we'd like to build, and think of this now as a generic schematic for any digital system, including your laptop or what have you. If you fly at a high enough altitude and look down, what you would see in a most generic way is a schematic in which we have this notion of a memory device which is keeping track of the current state, whatever it is. Now, of course, the current state of your laptop is actually quite complicated. There's a lot of it. Okay, so there's no implication that this particular memory device is either a single component or even a single type of component or even a small part. In other words, most of what we own in our laptops in one form or another is memory, and the processor, in terms of the total number of transistors involved and things like that, is actually a small percentage of the total number of transistors that you buy. Okay, so the memory stores the current state, and then we have this piece of combinational logic whose job it is to take the current value of the inputs, whatever they are in your system, and the current state, and the combinational logic figures out two things. It figures out what the next state should be, okay, and it figures out what the current output should be. And so we have this idea that we're going to compute these two things based on these two sets of inputs, the current state, which is coming out of the memory devices, and the current instantaneous value of the inputs. So what we want to do is then periodically come along and load that memory. We want to load the next state into the memory device so it becomes the current state. So there's sort of this notion of an instance in time, in fact, a sequence of instances in time, in which we'll be changing the state of the device, updating the state, and then we'll do it all again. We'll compute another state, which will be the state after the next update, so the so-called next state, new outputs, so forth and so on. In modern devices, we're doing this, a billion times a second, so this is a rapid process. If we actually looked at the current state and just said, listed out all the bits, we would see that there would be a sequence of values, hence the name sequential logic. Okay, so what we need is a loadable memory. And so we're going to spend the better part of the lecture designing the appropriate memory device. So we need a way to remember information. Well, we've been encoding information using voltages. So, low voltage is a zero. High voltage above VIH is considered a 1. And how do you what physical what are the ways in which we can store voltages? And one way is we can basically store a voltage as the voltage across a capacitor. We can move charge on and off the upper plate, and then we can look at the difference between the potential difference between the upper plate and the lower plate, the voltage across the capacitor. And if that voltage difference is high, we can store a 1. If that voltage difference is low, we can store a 0. Okay, so we can use our little NFET as a switch. So when we set the word line high, the switch is conducting or closed. And we can use that to go ahead and take whatever values on the bit line, either a high voltage or a low voltage, and use it to charge or discharge that capacitor. And then when we've got the capacitor at the value we want, we can set the word line to 0, which opens that NFET access switch. And now that capacitor, at least in ideal physics, will sit there for a long time. And that voltage will be there, and we can read it out by putting the bit line somewhere in the middle of its voltage range, again closing the access switch. And then because the capacitance of the bit line, we'd set the bit line, we'd charge the bit line. So it's a big capacitor. This is a little capacitor. And what we do is do charge sharing between the capacitors. And the amount of voltage change is proportional to the sizes of the different capacitances. So what we end up with is a tiny little voltage change. This is a very analog process, reading these things out. A tiny little voltage change on the order of millivolts. And we build very fancy circuits we call a sense amp, which actually looks for that tiny voltage change and says, aha, it must have been a 0 on the capacitor, the voltage went down a little bit. Or it says, aha, it must have been a 1 on the capacitor because the voltage went up a tiny little bit. So there's a lot of very fancy engineering that goes into making these circuits work. You own a zillion of these. This is basically dynamic RAM. The word dynamic should give you pause. Dynamic means changing. Storage and changing are not two words you like to use in the same sentence. The whole notion of storage is that it should store and not change. So in fact, even though these types of memories are very small, I'll tell you in 3 or 4 lectures, you'll see some pictures of what these DRAMs actually look like in terms of circuitry and stuff like that. But think of these as very small. You can buy billions and billions and billions of bits on a chip for not very much money. So this technology does work. It has a big downside, and it has several downsides. One is a pretty complex interface. So the writing, and most importantly, the reading is a fairly complex analog operation that has to be carefully timed. You have to be really careful of electrical noise. So getting these things to work, it turns out to be the work of decades to be able to make the capacitors very small so we can have a lot of them and still be able to reliably read and write bits. Stable, and here's why we call it dynamic memory. Sadly, charge will leak off of this capacitor. The dielectric here between the plates is not perfect. We can get leakage through that. More importantly, we can get leakage through the so-called sub-threshold conduction current. So sub-threshold means that the gate voltage is below the switching threshold of the NFET. So we think of it as off, but it's not really off. It just means that only picoamps will flow. But picoamps with very small capacitors means that charge will eventually leak away. And so we're able to sort of maintain that charge on the order of milliseconds. But every 10 milliseconds or so, if we don't go and read that charge out and then rewrite it completely, get it all recharged again, okay, we will lose the bit. So your dynamic memories are spending most of their life, not most of their life, but they're consistently about 10% of the memory bandwidth is being spent, basically doing these refresh operations. Not quite 10%, but a percentage of your memory bandwidth is being spent doing these refresh cycles where we're reading out all the bits and then writing them all back in. Okay, so this notion of refreshing seems to be important. This seems like a pretty complicated set of operations. Let's see if we can build a device where the refreshing happens constantly. So here's a circuit, a feedback circuit. So this is not a combinational circuit because it has a cycle. See the cycle? And it's the cycle that provides the refresh that we're looking for. It's a stable circuit. For example, if I put a 0 on this wire, the middle wire will be a 1, and then that is consistent with the output wire being 0. And as long as the device is plugged in, okay, the system will happily maintain those values, even if there's a little bit of noise. Because remember, the inputs here, are somewhat insensitive to noise. They'll still produce a valid output, even if the little bit of noise appears on the input. So the digital signaling discipline that we have that has noise margins makes this a very reliable, stable storage system. And in fact, it has two states. There's a second state, which involves, the ones and zeros being flipped around. That's also stable. Got it? So this is what we call a bistable storage element. It has two different states that are stable. And so what we would do is choose a particular wire, and we say the value on that wire is the logic value on that wire is the logic value that's being stored by this bistable storage element. And bistable is telling us it has one of two states. Actually, we can figure out sort of mathematically a model for what's happening here. This is the voltage. If I plot V in versus V out, so I'm thinking this now as a combinational system, these two inverters in a row, and that would, a low input voltage produces a low V out, high V in produces a high V out, so that's something like that. The feedback introduces a constraint, is that V in equals V out, and where these two curves intersect are possible, stable or possible states of the system. Those are places where V in equals V out. And the two on the edge are great because they're stable endpoints. Those are stable. Little variations in either this voltage or that voltage don't cause the system to change state. Okay. There is a slightly awkward solution to this equation, which is in the middle, and that's called a metastable point, which, as you might guess, means that it's stable, but maybe not reliably so. And in fact, that point will give us some difficulties. And at the end of next Tuesday's lecture, we'll deal with those difficulties. But for now, in the fondest traditions of wishful thinking, we'll pretend that doesn't exist, and we'll simply concern ourselves with the two stable states, which is how we're going to implement our storage. And then we'll adopt some discipline, another discipline that will guarantee that we don't end up in the metastable state by accident. Okay, so we're going to build a settable storage element using this multiplexer. Right? So the question is, this is great, this is stable, but how do I change the value? How do I get a value on one of those wires? Well, that's what the multiplexer is used for. So think of the multiplexer as something where this is the storage loop. If we think of the logic inside of the multiplexer, the AND and OR gate inside of here, what we would see is that when G is 0, we'd be selecting this input to become the value of the output. If we sort of looked at the logic there, it would basically form that loop, that bistable storage loop. So basically, when G is 0, you can see that the output value depends on the D0 input value, which of course is the output value. So that's the feedback mechanism, right? So this is not a combinational piece of logic. There's a feedback path. So this will be the only feedback we're going to allow ourselves, right? And in fact, you and I shouldn't do this. We should buy pre-built elements that have this feedback path built into them. As you'll see, they're called latches and registers. So this is called a latch. Okay, when G is 1, so in this state, the latch is said to be closed, okay, and basically in storage mode. When G is 1, G is the gate. Think of this as the gate. So the gate, when the gate is high, the latch is open or transparent. And any changes in the D value will be reflected on the Q output after a propagation delay. So when G is high, D gets passed through to Q. When G is low, it's in storage mode, and it's the high to low transition on G that changes from transparent to closed, and that's the moment we take our storage element, and as G goes down to 0, we're suddenly saying, whatever the value is on D at that moment, remember it now for a while for me, please. So this is the basis of our writable memory element. Is that a question in the back or just a, I'm sorry, people are not going to, they're going to sit there on their hands and be, I can't even scratch my ear without somebody. I'm trying to thread the line between being sensitive to the fact that there may be questions and being overly sensitive and causing everybody to go, wait, don't raise your hand above 3 feet, otherwise he looks at you. Okay. All right, so this is called a latch. In fact, it's called a D-latch. It's named after the name of the data input here. The schematic symbol looks like this. So all of these little boxes, think of this as a box that's holding a bit. And it's in holding the bit mode when G is low. Okay, and when G is high, we're letting information flow through. It's not so much the flow through that we want, except what we're trying to do is to get information to basically flow through to Q so that it will come back on that input, so we're all set to go into storage mode when G goes from high to low. Alrighty, so we can sort of see what's happening here is when G is high, after D changes, after a propagation delay of the latch, Q will reflect the current value of D. When G is low, okay, and you can see every time we make a change in D, if we wait for propagation delay, the answer comes out. When G goes low, what we want to do is to be able to say the value of Q will then be steady. Well, that would be the stored value that's coming out. And then after a little while, we're allowed to wiggle D, and it won't affect the stored value because the gate is closed, and we're no longer letting information through. Now, there is a small problem with this circuit that we need to think about, and we need to think carefully about it. The problem is, in general, with a piece of combinational logic, if you change any of the inputs, the output is allowed to go, do anything it wants between the contamination delay and the propagation delay. In other words, it's the only thing that the rules of being a combinational device give it the leeway to be a little bit flexible about what happens as it processes the new input value. It's only guaranteed to have a stable and valid output after the propagation delay. Well, that's not a good enough guarantee for us because we're using the output to remember the value. So if the output gets to go, do something strange, glitch or something like that, then we're going to be in a pickle because it's this output value that's going to form the basis of the value that we're remembering. So at least if we follow strictly the rules of combinational devices, this little red region represents an unknown value on the output, and this plan falls apart. So I want to make sure everybody understands that we're going to fix it, of course. We wouldn't get this far into a lecture with a bad idea. But does everybody appreciate why the plan falls apart without more rules about our latch? Yes? The width of this time is the difference between the propagation delay, which is that point in time at the end when it becomes valid, and the beginning of that red interval, which is the contamination delay, right? It's guaranteed to be valid for a little bit after an input change. That's the contamination delay, but then it's going to get to its new value. Okay, so we have this problem. The problem is that a change in an input value has potentially contaminated the output, and we need to fix that. So here's how we're going to fix it. Hopefully in recitation you discussed the notion of lenience. Lenience is the notion of a particular combinational circuit that when you have certain input values that guarantee the value of the output, you can wiggle the other inputs without contaminating the output. In other words, we can put the device into a configuration that certain inputs on certain changes on certain inputs no longer affect the output. The output will remain valid and stable even though you're changing a don't care input. The latch has three such intervals. One is that if G is 1 and D is stable, okay, that will get a valid value on Q after the propagation delay. In other words, when the latch is open, we don't care what's happening on this input. So the old value of Q will not affect the operation of the latch. Once the latch opens and information flows through the latch, the old remembered value no longer can affect the destiny of the latch, which is the output V1 after the contamination delay, after the propagation delay. A second region of stability is that if both D and Q, or in this Q and Q prime are just sort of two names for the same signal, if these two signals have the same value on them, you can wiggle G all you want, and the output will remain stable and valid. So these are properties that are true of a lenient latch. And in fact, in a previous lecture, we actually showed you the schematic for a lenient latch when we were talking about output glitches. Okay, and the third region of leniency that's interesting is that once G is low and Q is stable, once that's been true for a propagation delay, so a propagation delay after G going low, then D can change, and it will not, when the latch is in memory mode, So when we're basically going around this loop here, then we can wiggle D, and it won't affect the output. So those are 3 regions in which this carefully designed lenient latch will operate correctly even though, and have a stable output even though one of the inputs is changing. Okay, so as it turns out, designing feedback circuits, or so-called asynchronous mode sequential circuitry, is a very tricky business, and you have to be really careful. You have to, you might say, oh my God, this guy is Mr. Pedantic today. We're being super careful. And the answer is, well, you have to be, because once you get a feedback, if you mess up that feedback value, then all bets are off. So it's a tricky business, and we're trying to establish regions in which we can reliably change one of the inputs without affecting the other. And now on the next slide, I'll show you how to actually use that to build a reliable, settable storage element. So lenience doesn't particularly guarantee a working latch. We have to introduce one more set of constraints, and I'll show you what those constraints are. So to reliably latch a value into our latch, we first have to set up the value for at least, well, first we make D stable and valid, and after a propagation delay, the value of Q becomes stable and valid. So that means that this input now has just gotten a new stable value after the propagation delay. And then after another propagation delay, you can see it here, another propagation delay from here to here, that means that the latch now knows that this value and this value are the same. And we're now at a situation where we have one of those areas of leniency. We have after waiting 2 propagation delays, every part of the latch now knows that Q prime and D are the same value. So those 2 propagation delays, they have a very specific name. We haven't changed G yet. How long does D have to be stable and valid before we change G? It's called the setup time of the latch. And we sort of give you an argument of why 2 propagation delays should be enough. Most latches actually have a setup time that's less than 2 of their propagation delays, but we're just doing a sort of a conservative argument that argues that 2 propagation delays will certainly be enough. So at this stage, with both Q prime and D having been stable now for an entire TPD, we can change G from high to low with a guarantee that the Q output will not be affected by that change. So now we can go ahead and put this low, like that. And if D remains stable for another propagation delay, we're now once this goes low, once we give another propagation delay here, right, we're in a situation now where for an entire propagation delay, G has been low and Q has been stable, and now D can change all at once. And we're in another one of those lenient regions where we can be pretty sure that, or we know that the latch will be stable and valid if we wait at least 1 propagation delay before changing the D value. And so these are 2 magic, so this time after the rising clock edge, okay, after the falling gate, I'm sorry, I'll get to rising clock edge just in a minute. After the falling edge of G, okay, it's called the hold time. So there's a region of stability which will guarantee that our memory system will remember exactly what we hope it will remember. And we're requiring that D be stable, T set up before going into memory mode, the transition from high to low, and T hold after that transition. So the setup and hold time. So every storage element that you buy will come with a spec sheet that will give you the setup and hold time. And that's telling you that the input value has to be stable for some amount of time before you close the latch and stable for some amount of time after you close the latch. And if you meet this with the so-called dynamic discipline, the setup and hold times, in fact, the latch will store the value that's been stable, the stable value that's been on that input. What should you expect to happen if you violate the dynamic discipline? If you end up changing D, okay, sort of, inside of this required region of stability, what would you say would happen in the circuit? Would you be able to tell me what value was being stored? Yeah.
We're not sure, but I think we're not sure what the value might be, but
Right, so at the very least, we can't make any guarantees about the value that's being saved. It might be the older value of D, or it might be the newer value of D. We're not quite sure when exactly in here that the feedback loop actually gets closed. There's some propagation delays in internal circuitry. So what we're doing here is we won't be able to tell what the value that's being stored is. Turns out that's the good news. The bad news is the device may not even produce a digital output for an arbitrary period of time. And that has to do with that metastable point. So keep that in mind. We'll come back to that. That little teaser there. So not only can we not guarantee that we know what value will be stored if we violate the dynamic discipline, we can't even guarantee that it will produce it is no longer a digital device. And that turns out to be a pretty awful circumstance that we'll avoid at all costs. Okay, so bottom line, stable T setup before the transition into storage mode, and T hold after the transition, so the setup and hold times. So those are concepts that any digital engineer is very familiar with. So let's try it out. We'll put a latch into our system. We'll put a little open the latch and then close it again. And when we open the latch, we basically will take the next state and start, we're in the process. This little high period is an attempt to write the next state value into our little storage box here, so it becomes the current state. So it turns out that as soon as this is open, though, we have a combinational loop now on our circuit with our loop. Right, so there is a storage loop inside of here, which is what we're seeing when G is low. But when G is high, we have a different loop, which is this big loop through our big combinational logic cloud. And that is a little bit awkward, because once we create a loop in the circuit, we can get oscillatory behavior. We can get all sorts of bad things will happen. And so if we leave this high too long, the next state becomes the current state, and the logic says, oh, quick, a new state, I'll compute the next state after that, and that becomes the next state, and zoom, zoom, zoom all the way around the circuit. All of a sudden, everything's happening at once. So even though the latch was a good storage element, in this application it's failing, because we have to be really, really clever about opening it for long enough to get the value to be stored reliably, but not long enough to find its way all the way around the loop and have the D input start changing as a result of the new output value that you let through when you open the latch. Okay, so the bottom line is, I think Mr. Blue has it right, this is a stupid approach. I mean, you could try to be clever, but the whole point behind digital logic is we can prove it works. It's not based on some, if you're quick just the right way, it'll work. It's very reliable, and this is not a very reliable memory system. Okay, so we need to come up with a better storage element. We've got a good start, but we need to fix this. Okay, so here's an analogy that will help us understand our fix. You have a bunch of cars waiting at a toll gate. Okay, so let's all drive over to the Sumner Tunnel after lecture. We'll all line up behind each other, and we're gonna cheat Massport. And how are we gonna do that? The gate will open, and we'll all drive through. It'd be like a really long car. So if these were a set of states, a sequence of values that we hoped, the set of states that we hope to go through, you can sort of see this notion of having a single gate that opens. It's hard to say, look, only one car was supposed to go through. Why did three of you, step on the gas pedal and fake us out? Okay, so that's sort of a mechanical analogy of what's wrong with our system. Now, how would you fix it if you were Massport and had to build a toll booth that would let one car through at a time? Okay, the answer is we could use two gates. Okay, and we would arrange it so that it was never the case that both gates were open at the same time. So initially what we would do is have gate 1 open and gate 2 closed. Okay, and a single car could get in. But before opening gate 2, we would close gate 1 and then open gate 2. And now we get exactly one car through the system. There's no path by which more than one car, without busting a gate, okay, but there's never a clear path from the waiting line to the output road, okay, in which people could rush through. We're always guaranteed that at least one of the gates is closed. Have you ever looked at a mechanical clock? So there's a big gear that's actually attached to the wind-up spring. Have you ever looked at the mechanism that is used to make sure that a gear only advances a little bit? Okay, why it is when it wants to go tick, it doesn't go bzzz, and 2 days pass all in a hurry? And the answer is there's this tiny little rocker arm that's going back and forth, okay, and it's set up so that the spacing of the little teeth that it's sticking into the gear is such that it will only let the big powered gear, the gear powered by the spring, advance by one tooth. Right, so the second, when you open this guy to let the gear advance, the second tooth comes down and basically catches another tooth of the gear after it's transitioned by exactly one tooth. And so this thing is going back and forth like this. That's called the escapement of a clock. So this is really, and it's just like a clock escapement. It's basically letting one bit through at a time. So 2 gates. If a latch corresponds to one of these toll gates, the circuitry we want to design, okay, involves 2 latches. And they're arranged, we have a signal here that we now call a clock signal because you'll see we're interested in a particular edge of the clock. So clocks have edges, gates have levels. Okay, so this will now be called an edge-triggered device. You'll see why we call it edge-triggered in just a moment. But the idea is that when this guy is open, the master is open, the slave is closed. When the master is closed, the slave is open. So these are the 2 things. And you can see that they're working off of opposite ends. What they're using as the gate is the different phases of the clock. So this is exactly the picture from the previous page, except for bits. Okay, so we have this sort of mechanism that's guaranteeing that they're not both open at the same time. There's never a combinational path to the register. So this is a thing that people often forget, that there's no relationship between the timing of the D signal and the timing of the Q signal. The Q signals, the value and the timing of the Q signal is determined completely by logic inside of this combination of these 2 latches, which we now call a register. And so even though D has to meet the setup and hold time of the master latch in order for the things to work correctly, the timing of Q is only determined by the slave latch. It's never connected directly to D. So these registers sort of represent the beginning and end of timing chains in our circuitry. Okay, if you're worried about the inverter and there might be a little delay and maybe for particular clock edges there's a case when both this signal and that signal are both 0 or both 1 because of the delay of the inverter, we don't need the inverter. We can simply wire up the master latch slightly differently in terms of where the feedback loop is connected and where D is connected and get an inverting gate that way. So no extra inverters are actually needed. Okay, and so if we look at the waveforms, here's D wiggling up and down, here's the clock, and we can actually try to understand how this circuit is working. So when the clock is high, the master is closed. So in this period here, the master is closed. And you can see that because the master is closed, D can wiggle, but because when clock is high, the latch is closed, D can wiggle, but Q, it's the star output, which is the Q output of the master latch, is unchanged. When the clock is low, the master is open, okay, which means you can see the star signal is now wiggling every time the D signal changes, because now the master is open in this region. Okay, but since the slave latch is closed in this region, the Q output, here we go, the Q output here remains stable. Because the slave is closed in this region, the Q output remains stable. So if we looked at this, when is the only time the value on the Q output changes? The only time the Q output changes is the moment in time at which the slave latch opens, which happens on the rising edge of the clock. As this clock makes this transition here, the value of Q will change, but then because of the rest of the escapement mechanism, it will remain stable until the next rising edge of the clock. You can sort of work through the waveforms and see how this works. What I'm trying to convince you of is that this appears to be an edge-triggered device. It's nothing in here, it's looking at edges. Everything is our gates being controlled by levels, but we've organized things so that the output only changes right after the rising edge of the clock, hence the name edge-triggered, right? Because it only changes right after the rising clock edge. So at the rising clock edge, we sample thinking of this now as a big device, the current value of D, the stable value of D, this meeting the setup and hold time, is sampled by the master latch, okay, and becomes the value of the star, the internal node here. And then on the falling edge, the current value of that star node is sampled by the slave latch and becomes the value of Q. Okay. So we draw this. It looks just like, it's another one of our storage boxes. It has a D input and a Q output. But we put this little triangle here to remind ourselves that this is an edge-triggered device. So over here, no edge, this was just an ordinary input. Over here we have a little triangle. That reminds us that this is now an edge-triggered device, a positive edge-triggered D register. Sometimes people call these flip-flops because they're either in one of two states, flip and flop. Okay, 0 on the output or 1 on the output. But the modern name is D register. Everybody happy with D registers? Takes a little, thinking about how it works takes a little thing. Now, as it turns out, there's a little, we're having a state here where what's happening is that the master is opening just at the same time that the slave is closing. That happens at the falling edge of the clock. So the master signal will start to change because the master latch is opening right at this clock edge. And the slave latch is trying to go into storage mode. So we have this little sticky wicket where we have to worry about that, making sure that the master's contamination delay, how long star stays valid, is long enough to meet the hold time of the slave latch. If that's not true, you throw everything away and start again. I'm raising my hand because I'm a member of that happy club of electronics designers that happens to have built a register where on an occasional Tuesday that wasn't true. Okay, and it turned out that the register did not work reliably. Okay, and we had to replace a lot of electronic circuitry as a result. Never a pleasant conversation to have with your VP. Hi, I've discovered this awful bug. You know those 100,000 units you were so proud of shipping last week? It turns out they're broken. Now, if I worked for, Takata Airbag, everybody would say, "Psst, don't tell anybody, maybe no one will notice." But that's not that's not how us engineers do things, right? So a good engineer will fess up to your errors as soon as you find them, and so that everybody can work together to find a solution that keeps people. Mostly people are forgiving. What they're not forgiving about is when you hide something from them and try to cover it up. That's almost the worst thing you can do in engineering. So if you do a lot of engineering, you're destined to make a few mistakes. Own up to them, work hard to get them fixed, and learn your lesson. And typically your engineering managers will then take you out for a beer and explain their story about when they made their mistake, because we all do. So that's so I learned some lessons. Mostly what I learned is don't try to design your own registers. Buy them from buy them from the manufacturer who already has circuits that they guarantee will work. And at least if it doesn't work, they don't shoot you. So that's a good thing. Okay, so here's the timing for a register. It looks as follows here. What we have is, I'm looking at the Q, here's the Q output. It changes after the rising edge of the clock. It's valid for some length of time. So, and so it stays valid with its old value for the contamination delay of the register. And then after the propagation delay of the register, it becomes valid with the new value. Okay, registers are lenient in the sense that they're always designed so that the value isn't changing. There's no glitches on the output. Everything is measured relative to the rising edge of the clock. Has nothing to do with D. D, on the other hand, has its own timing constraints. There's a setup time and a hold time that you have to meet. Otherwise, the register will not work correctly, as I'm here to tell you. Okay, so everybody sort of get that? So those are the 4 timing numbers. When you buy a register, they come up with a contamination delay. A lot of manufacturers call that the minimum propagation delay. I don't know why, but they do. They haven't taken 004. And then an actual TPD, a propagation delay, which tells you how long until the new value comes out. And then the setup and hold times. And that's what you need to do the engineering. Okay, so our scheme is we're going to build our one clock throughout our whole system. That's how we in 004 will do it. It makes life very simple because that means we basically build combinational logic. That's what these clouds are. No cycles. The only cycles anywhere in the circuit are the ones built into the feedback loops of the registers. Okay, that's the only cycle we allow ourselves. That means we can establish the length of time it will take from any register output. We can compute the maximum TPD to any register input. And we just make sure that the distance between the time between rising edges of the clock is enough time for everything that has to happen in terms of calculations between new register values and next register values happens completely in one clock cycle. If it doesn't, I can make the clock cycle longer to make sure that there is enough time for everything to happen. And that's what happens when Intel sells you, a 1 gigahertz processor or a 1.5 gigahertz processor. It's the same design. It's just that some parts of some chips come out hot. They run quite a bit faster than other chips. Typically, the chips closer to the center of this big wafer they're doing actually have higher performance than the ones at the edge. So the ones at the edge, they sell you as slow processors, and the one in the middle, they sell you as fast processors and charge you twice as much. So it's a good deal. Make good use of all the silicon they can make that is at least functional. Okay, so the single clock discipline is there are no combinational cycles except the ones that are built into the registers. We have one clock that goes everywhere. That makes it very easy to basically do all these calculations of doing the arithmetic about how long I have to wait between clock edges to guarantee my circuit will work correctly, to make sure that the values are stable, T set up before and T hold after the clock edge. We only care about the values on the inputs to the register just before the rising clock edge. So this can be glitchy logic. It doesn't matter because their values are only being consumed by the register, and the register only cares at the rising clock edge, or T set up before the rising clock edge. Okay, so we don't have to be careful about glitches and stuff like that unless we're worried about power dissipation. Okay. All right, so let's take a quick moment, and we're going to go over this tomorrow in recitation much more slowly. But the idea is that we can be very careful. We have a synchronous system. So we have a register, an upstream register and a downstream register. The values come out of a register. They go through some combinational logic and go into a downstream register. We can be careful about what the timing of this is. And we'll discover there's two timing constraints that we as engineers have to worry about. First of all, let's look at the timing for the Q1 output. So after the rising clock edge, the old value remains valid for the contamination delay. Then the QR1 changes until it becomes stable and valid again after the propagation delay. So it stays valid, the old value stays valid for a little bit, and then we have a period of change. And at some point in the clock cycle, after the rising clock edge, I get a new and stable valid out of the register. And that's determined by the propagation delay of register 1, TPD reg 1. Now let's see what happens when that signal passes through the combinational logic, okay, and ends up here in the star node. You can see that, well, the combinational logic has its own contamination delay. So the star node remains valid now for the sum of the two contamination delays, the contamination delay of the register and the contamination delay of the logic. So star remains stable for a while, okay, and then after when QR1 becomes stable, at this point, we wait for the propagation delay of the logic, and now star becomes stable and valid. And we know that that has to be true, okay, at least T setup before the next rising clock edge. So we can end up with these two timing constraints. If we think about the star node, it remains stable and valid after the rising clock edge for the sum of the two contamination delays. In other words, this period of time in here, T1, basically has to be longer than the hold time of the register, of the downstream register, in order for this system to work. The second constraint, which is coming out of the register to get a new value stable, through the logic to get a new stable value on the input, plus T setup, all has to fit within a clock cycle. So I can't have the next clock edge until I've gotten the new value out of the old register, computed a new value for the input, and have it be stable for T setup. So the sum of all of these values has to be less than the clock cycle. So the message is that these are two timing constraints that must be met for a synchronous circuit to work. The bottom one you can always fix by making the clock cycle longer so that that inequality is true. The top one If it doesn't work, you throw it away and you restart, because there's no external signal that's determining the contamination delays. That has to intrinsic with the design of the logic. So if you violate the first timing constraint, okay, you have to go pay another $1 million to get a new just redesign your circuitry and rebuild the integrated circuit. Very expensive, very time consuming. It's just very bad. Okay, so people put a lot of effort into making sure they do that. This, you want to do the best job you can, but you can always set the clock cycle to solve any other remaining problems. So you actually have in your possession a CAD tool that you'll use, the timing analyzer inside of Jade, which actually performs these calculations for every register-to-register path. And when you're designing your own processor, you'll use it to figure out how fast your processor is, and then figure out how to make it even faster. Alrighty, I'll stop there. Good luck on Lab 1. See you in section tomorrow and lecture next Tuesday.